The results open possibilities for studying gravity's effects on relatively large objects in quantum states. Now, for the first time, scientists at MIT and elsewhere have cooled a large, human-scale object to close to its motional ground state. The object isn't tangible in the sense of being situated at one location, but is the combined motion of 4 separate objects, each weighing about 40 kilograms. The object that the researchers cooled has an estimated mass of about 10 kilograms, and comprises about 1 by 1026, or nearly 1 octillion, atoms. Their results, appearing today in Science, represent the largest object to be cooled to close to its motional ground state. The scientists say they now have a chance to observe the effect of gravity on a massive quantum object. This finally opens the door to an experimental study of how gravity might affect large quantum objects, something hitherto only dreamed of. To stop an object in its tracks, one can exert upon it an equal and opposite force. Physicists have applied feedback cooling through various means, including laser light, to bring individual atoms and ultralight objects to their quantum ground states, and have attempted to supercool progressively larger objects, to study quantum effects in bigger, traditionally classical systems. To cool the atoms of a large object to near ground state, one would first have to measure their motion with extreme precision, to know the degree of pushback required to stop this motion. LIGO, as it happens, can. A laser at the tunnel's nexus is split and sent down each tunnel, then reflected back to its source. Soudier and his colleagues wondered whether they could use LIGO's motion measuring precision to first measure the motion of large, human-scale objects, then apply a counteracting force, opposite to what they measure, to bring the objects to their ground state. The object they aim to cool is not an individual mirror, but rather the combined motion of all 4 of LIGO's mirrors. It turns out you can map the joint motion of these masses mathematically, and think of them as the motion of a single 10-kilogram object. As individual photons of a laser bounce off a mirror to gather information about its motion, the photon's momentum pushes back on the mirror. Soudier and his colleagues realized that if the mirrors are continuously measured, as they are in LIGO, the random recoil from past photons can be observed in the information carried by later photons. Armed with a complete record of both quantum and classical disturbances on each mirror, the researchers applied an equal and opposite force with electromagnets attached to the back of each mirror. The effect pulled the collective motion to a near standstill, leaving the mirrors with so little energy that they moved no more than 10 to 20 meters, less than 1,000th the size of a proton. The team then equated the object's remaining energy, or motion, with temperature, and found the object was sitting at 77 nanokelvins, very close to its motional ground state, which they predict to be 10 nanokelvins. This is comparable to the temperature atomic physicists cool their atoms to get to their ground state, and that's with a small cloud of maybe a million atoms, weighing picograms, Soudier says.